This is for the
3.1.
It is. It says it.
it's for this all the track kids that weren't here today. Hopefully
That's
this will be a
cross-country, though.
successful
It's cross country.
recording.
41.
Yeah, we're starting. Or this is section 3.2.
Oh, really?
Rules and the mean value theorems. Okay, I'm going to draw for you a couple of pictures that I want you to associate with these two theorems, and we will discuss some lucid examples and call it a day. All right, so let me start. All right, let's start with Rolle's theorem. Rolle's theorem says this, that if you've got a continuous function on some closed interval, and differentiable on the open interval. All right, one more and f of a equals f of b. Okay, so there are three conditions there. Really, the first two conditions here can be kind of rolled into one condition here. Remember that the only reason he says continuous on the closed and differentiable on the open is because we technically are not differentiable at the endpoints. Okay, but if I've got something like this picture illustrates here, notice that it's not only continuous, but it's smooth everywhere. You see that? All right, smoothness. Differentiability should associate with smoothness. And not only that, but f of a, all right, equals f of b. Okay, so when that is the case, what Professor Rolls said is that there's got to be at least one value of c inside this open interval.
Which is equal to f of a and f of b.
No, where the derivative at c is 0. Okay. So, in other words, in order to return, if you start here at f of a, just think about this as a path. In order to get back to that same y value, if the function is smooth, it's got to pass through a point where the derivative there is 0. Okay? All right, so then there exists a c in the open interval such that f prime of c is 0. Now, in the drawing that we did, there's actually 3, right? So there's c1, here's another guy, c2, and here's a third guy, c3. But this is what we call an existence theorem. It just ensures that there's at least one. All right. When we say there exists, another way to say that is there's at least one value that makes this true. F prime, which is 0. All right. That's Rolle's theorem. We use Rolle's theorem in the proof of the mean value theorem. However, I know you like to see proofs, and I like to do them too. We just don't have the time. I'm just going to go ahead and give you the mean value theorem, and then we'll use it. All right. I just want to take today on this section. I don't want to take more than a day on this. So.
I out of curiosity, on proofs like this, where it's existence, how do they do, is there, like, how are they proving it? Is it just they do it, like, by cases, or
Yeah, for Rolle's theorem, it is another one of those case,
case that?
yeah, where he just shows you, I think, the cases involved. He gives us a couple cases. All right, so let me just let me shrink this down a little bit. Okay. All right. So let's consider now the mean value theorem. The mean value theorem is actually very similar. So you've got a function. It's going to be continuous on AB. So let f be continuous on the closed interval A to B, and again differentiable differentiable. Hope you can read that. I don't like that. Let me fix that. Hey, differentiability though. Remember this. That's our strongest conditions. We don't have a condition right now any stronger than differentiable. The only one that in calculus you really can do is you can just go differentiability in terms of the order. So like is the derivative differentiable, and is the second derivative differentiable, and so on. Okay. So let f be continuous on AB and differentiable on the open interval. Okay. Now the condition, the only difference here is that we don't have to have, for the mean value theorem, we don't need to let f of A equal f of B. In fact, I hope you're going to see how Rolle's theorem really is a special case of the mean value theorem. So that's all. Those are the only conditions we want. We want continuity. We want differentiability. So let's create such a function. Okay. What the mean value theorem says is this: if you've got these conditions, all right, f of A does not have to equal f of B, then there exists a C in the open such that f prime of C is equal to, and this is, what does mean mean?
Average.
Average.
Yeah.
Good, it's equal to the average rate of change. Remember what f prime means. F prime means the instantaneous rate of change, all right? So according to the mean value theorem, there's an actual value in the open interval where the instantaneous rate of change there is actually equal to the average rate of change on the interval, which would be f of B minus f of A all over B minus A. So graphically, how would we illustrate that?
Maybe the secant line between A and B would be your average.
Yeah, good. All right, it would be, what we're saying is that the average rate of change from A to B, okay, there's got to be a point in there, at least one, whose instantaneous rate of change, or at which the instantaneous rate of change is equal to the average rate. So what we would be looking for are points who would have points where the tangent line is parallel to that guy. All right, so and again, just from this drawing, you can see that there's at least a couple of them, right? Yeah, there's two. Okay. Yeah. So again, in the picture, there's two, C1. But again, it's the theorem itself is an existence theorem. All it is stating is that there has to be at least one. Right? This is called the mean value theorem.
And what's it? It's like f is f prime.
What, buddy?
Would you it's the difference between an average rate of change and a instantaneous?
Yeah, instantaneous. Yeah, average. Yeah, good, John. I'm glad you said that. Let me me write that at the bottom.
Oh, there.
Instantaneous rate of change. Right, instantaneous rate and average rate. Okay. Yeah, this guy you got in algebra, at some point.
We should really come.
Yeah.
We never talked specifically about like what defines the secant log, but we did this year.
Well, really, I would think that at some point you would have defined that as average rate somewhere, no? Okay, maybe not. Maybe not. Okay, that's a definition. This is how we define, that's how we define average rate of change. Okay, all right, those are the theorems. That's it really for the notes. Let's take a look at some problems here.
You were in fourth period algebra too, right? You went to eighth period. Did you? No, I went to eighth period. That was just.
I was just in the back of
Oh, that's right. You were just in here.
because like I got bored like during the matrices because I had already learned it, so then I was just like, I will do it.
Yeah, I think we just all sat. We just came the whole time.
Okay, take a look at number 7, f of x
You
is
then
equal
came just
to.
messing with you.
Shouldn't we be taking notes?
It came from yeah, I remember taking notes.
Yeah, Kate just sits
I'm gonna
there.
corrupt this file and delete it.
Kate, I'm not sure if you can hear the voice teasing you back here. Anyway, okay. Dr. Larson wants to know whether Rolle's theorem applies here. If it does, he wants you to find the C values that satisfy the, or that are guaranteed by the theorem.
Is it asking for roles? So more specifically?
Rolle's theorem, yeah, and Rolle's theorem demands really two things, really. It demands differentiability and then also that f of a is equal to f of b. So let's check that last one. What about this? F of a equals f of b. Well, so f of -8, what is that? Remember, whenever you're taking a rational power, you should do the root first if it's convenient. What's the cube root of -8? Good. -2, then squared. 4 minus 1 is 3. And then if you do that with 8, you're going to get the same thing.
Wait, would you say you square first and then cube?
You don't have.
You
Yeah,
can.
because that gets rid of it. if
You
there is-
can do that.
It works.
But by definition, you should be able to do both in both directions. And you're always going to be able to do that. The only question I think.
Like if you have
Well, you'd get a negative I, but that would be squared up.
like -1 to the 4.
Yeah, if you had a power that was it wasn't a reduced fraction, and they were both they're both evens, then I don't think you'd ever see that. But technically, though, that one would be a weird one. That'd be a
It'd
weird
be
situation.
complex and then it would, yeah. But it should always reduce anyways.
Yeah. So I'm not sure if I've ever seen that kind of case. You know, where they left it unsimplified for a specific reason. Anyway. Okay, so f of -8 equals f of a. So that part's good, right? F of a is equal to f of b. All right, what about differentiability? What about f prime? What is f prime?
Well, this is a, oh no, my fault, there's roots in this.
So 2/3 x to the what? -1/3, right? And here again is a good illustration of why negative exponents can be a little bit tricky, right? Because that x there is really where?
On the bottom.
It's in the bottom of the fraction, yeah. So now comment on this. Is this guy differentiable everywhere on the interval?
Cube roots, yeah.
Not everywhere is x on the bottom, so if you have 0.
Good.
Oh yeah, you're right.
If x is 0, it's going to blow up, right? And 0 is in this interval. So therefore, f prime of 0 is undefined. So Rolle's theorem can't apply. Okay, is that cool? Not differentiable on that interval. All right, what about this guy?
Every time I see this Rolle's theorem, I think of Rolls Royce.
Okay, Richard.
Is that how you spell it?
No. It's spelled
What about this guy?
differently. Is this for Rolle's theorem?
Rolle's theorem again, yeah, sorry, on 0 to pi over 6.
Even.
What is it? Pi 0 pi?
Well, let's check to see if the function values at the endpoints of the interval are equal to each other. So, does f of a equal f of b? So f of 0, what's f of 0?
0.
So sine squared of 0 is 0.
Yeah, it is 0, right? Sine of 0 is 0, 0 squared is, yeah, and then this is 0. So yeah, f of 0 is 0. What about f of pi over 6? Yeah, very good. Okay, so if you plug in pi over 6 here, 6 over pi times pi over 6 is 1. Minus 4 times, what's the sign?
1/2.
Good, half.
1/4 times 4 is 1.
Yeah, good. So, yeah, so half squared, right, is 1/4 times 4 is 1, 1 minus 1 is 0, yeah. Okay, so check, that condition is met.
Now, what is the derivatives of the?
Yeah, and what do you know about a polynomial in the sine? They're differentiable everywhere.
Yeah.
Okay, there's no issues there at all. Sine, derivative,
Exactly.
cosine, Okay, so this guy is differentiable. So f is differentiable everywhere. All right, so according to Rolle's, there exists a C in the open. Here, let me use pi over 6. Let me use 0 to pi over 6. A C in 0 to pi over 6, such that
What does it mean when there's differentiable everywhere again?
it means the derivative exists everywhere. Good, that's a good question. It means when you take the derivative, there's no place where it doesn't exist.
Okay.
All
So
right,
we usually
good.
think of it being like smooth. Remember how the absolute value
There
doesn't have
exists a
one because
C
it's all
there,
up?
such
Oh,
that,
yeah.
Yeah.
such that f prime of C is equal to 0. Okay, so how do I find these C's?
Plug in, derive it and then
You
plug
take
in
the
zero.
derivative. Yeah, good. Take the derivative and then set it equal to 0. Okay, so f prime here is equal to what? What's f prime equal to?
It'd be 6 over pi minus
Good, that's a coefficient on x, right? So 6 over pi.
8 sine x times cosine.
Good, yeah,
Times
6
x.
over, very good. 6 over pi, all right? 6 over pi minus 8 sine x, and chain rule, right? Times cosine x. All right, equals 0. Okay, what's bad about that equation? This is what Nick, this is what
Oh, yeah.
Rolle's guarantees, if the conditions are met, Rolle's guarantees that there should be a value that satisfies that.
You have to mess with the trigonometry.
Yeah, right. This is a situation that, and I think I've mentioned this to you for whatever reason. Well, I guess this is a good example of why it does come up. Is when you're dealing with a sine squared, you're taking the derivative, you end up getting a 2 sine cosine out, which is
Oh, that's the sine x cosine x, right? That's
yeah, 2
two
sine
x
cosine. That's the double angle formula.
So it would be
Yeah, for
sine
sine.
x, right?
Yeah, very good. So
Four
this
sine two.
this is good. This is the same thing as 4 times times 2 sine cosine. So you can rewrite this guy now, let's go to black here, as 6 over pi minus 4 sine 2x. Okay, equals 0. All right, so the 4 comes out. If you slide a 4 out of that, you're left with 2 sine cosine, which is sine 2x. It's a double angle formula. Once in a while, man, that formula, well, yeah, you need to see why. When you take the derivative of sine squared, it just pops out. So it's a good one to remember, okay? All right, so if I solve this, what do I get?
Would be sine 2x equals 3 over 2.
Yeah, good. I gotta divide off the 4. So once I do that, divide by 4. So you get 3 over 2 pi, not 3 halves pi, but 3 over 2 pi. Okay, like that equals sine 2x. Okay, tell me about that equation. Now remember, hey, let's go back here for a minute. Remember that that x is in here, 0 to pi over 6, right? X is in that interval. Okay, so if x, let's put a note over here, since x is in 0 to pi over 6, then 2x is in 0 to pi over 3. So your initial search is, remember your initial search, because of the 2 on the x, the initial search is going to be twice the sum. The initial search is going to be over an interval that's twice as large as the original interval.
That, like the sine 2x, the 2 would compress its sine graph, right?
Yeah, good. That's right. So you potentially have twice the amount of solutions as you
In
would.
that one.
Yeah. I mean, you don't necessarily, but this is just because you smash it by a factor of 2 doesn't mean that this particular interval is going to pick up an extra solution. Yeah. However, okay, that's good thinking on that. That's exactly what it does. So how do I go about and actually find the values at all that satisfy this? How do I find where sine, cover that 2x up for a minute. How do I find where sine is equal to that ratio? What's that? Yeah, good. Why?
Because
Why do I need arc sine here?
it doesn't care what value. One, we know it's going to be in the first quadrant, so we know.
Yeah, okay, so 0 to pi, right? But we know it can't be here, right? Why? Yeah, that's outside, right? That's outside of this interval 0 to pi over 3. So you're only looking over here, somewhere in between 0 and 60, you're looking for a solution there. But because the ratio's not nice, right? 3 over 2 pi is not a nice ratio. So we will do arc sine. Because no, and this is tricky.
There's a pi on the bottom.
Pi's on the bottom, not in the top. That's why. Okay? It is kind of bizarre that way. That's how I rewrote it.
No, you.
Yeah, okay. Pi's on the bottom. So arc sine, right, of 3 over 2 pi is equal to 2x. So because arc sine sends all of its positive ratios back to this first quadrant, then I know that's the only solution you're going to get. So,
Isn't it negative 6 over pi? No. I mean, well, I'm assuming. Oh, you just added. Okay, I see what you did. You added over 4 sine 2x. Sorry, you weren't dealing with negatives. That makes sense.
oh, okay, yeah, just move that there. Okay, so if you were to punch that out, okay, thanks, Matt. Yeah, make sure you're right, yeah. Now be careful how you write that. 3 over 22 pi?
3 over 2 pi.
Gotcha.
0.498.
Yeah, that's cool. Okay. And then, so divide by 2. So 249. Yeah. And that's it. That's the lone answer there. Okay. Anything else would have been outside the 0 to pi over 3 range, yeah. Okay, is that cool? That's a good one to do, especially because you have to solve a trig equation. Okay. Okay. Take a look at. All right, let's look at a couple mean value theorem problems, and then we'll do a couple multiple choice or a couple true falses, and we'll be done. Sorry, I always get panicky about the time.
You have another like 10, 15 minutes?
2:42. Okay, 42. Yeah, about 15 minutes. Okay, number 30. Dr. Larson's asking the same thing, except this time it's about the mean value theorem.
Some more general.
Yeah, if you think about it, if you go back and you look at the pictures that we drew, you'll see that that if f of a were equal to f of b, and you happen not to even check that situation, and you applied the mean value theorem, what's f of b minus f of a?
It'd be 0.
It'd be 0, so you still end up having the derivative equal to 0, like the Rolle's theorem says.
Which makes sense because that flat, the connection between the flat and
Yeah, exactly. Yeah, that's right. So it does sort of beg the question, though, why you don't prove the mean value theorem first. But Larson presents the Rolle's theorem first. I think most guys do, and they prove the cases involved there, and then use that result to prove the mean value theorem.
I guess going from a specific case and then generalizing it might be easier.
Yeah, that's
So
a
you're
good
not going from
question.
such a broad concept to
Yeah.
a narrow one.
Yeah, that's a good point, John. That's a good
It's easier to
point.
build up to it.
To use a situation where all you're saying is that f of b, well, yeah, it might be like that, John. It might be that because the specific situation is a little bit more, maybe more easy to write out, and then to look at those cases, you can adjust that situation to fit a general situation maybe easier than from the other way. Yeah, it's a good call. I'm guessing that is probably true. Okay, look at 30. F of x equals x plus 1 over x, and this is on this interval. Okay, again, it's mean value theorem. You do not have to worry about f of b equaling f of a. Is this guy differentiable on the interval?
No. Just stuff over here.
On the interval.
On the interval, yeah, it is, because the only issue that would happen
Oh,
is that
zero.
x is 0. Yeah, and that's not in our interval. All right, but before we ever apply the differential operators, yeah, I feel for you. I'm tired.
Yeah, he's looking for you back.
Yeah, it's fine. I stayed up and watched that game, man.
Where's the sound? Oh.
See, that was the computer.
Because I was about to say, if it was a computer, the
Okay, so f is differentiable on f2. Notice I'm not even paying attention really to the continuity requirements at the endpoints, because these guys don't have issues at endpoints unless you're, again, hitting 0 or x is 0 or something like that. So that I'm just going to mention f is differentiable on that. Okay, so I now have to do what? I now am going to, in applying the NVT, so therefore, the mean value theorem, all right, guarantees, I don't know how to spell guarantees, G-U-A or G-A-U? G-U-A. Guarantees the existence
Some people specific derivative equal to the average.
of C in that open interval, such that f prime of C is equal to the average rate of change in that open interval, or that closed interval. F of, 2b minus f of a. Yeah, let me use those values, John. I like that. That's good. F of 2 minus f of half all over 2 minus half, right? Okay, that's what the mean value theorem says. Okay, what is f of 2? Oh, by the way, well, we can, okay, let's just do the right-hand side right now. What's f of 2?
So 3 over 2.
Yeah, 3 halves. Good, so this is equal to 3 halves. Minus, what's f of half? Yeah, this is a case too where you might want to. I was gonna let this go until we took the derivative, but remember before we apply any differential operators, you really should simplify. So that x can go into both those terms. So this is equal to 1 plus 1 over x. I'm just going to note it now. F of half is 1 plus 2 is 3, yeah. So this is equal to minus 3. All over 2 minus a half is 3 halves. All right, so that's 1 minus 2, right? Okay, so that's f prime of c, and that should equal to that should be equal to f prime of c. Okay, so let's take the derivative now.
Equal to negative.
So yeah, instead of equal to -1, so f prime. Well, let's see. Anyway, f is equal to 1 plus 1 over x. Again, a little bit easier to handle the derivative like this. So what's f prime?
Just x.
What is it?
So negative 1 over x squared.
Yeah, -1 over x squared. Correct.
Oh, that's the simplified version.
That's the, yeah.
That's the original.
They like the Montgomery.
Yeah, I heard about that. Were they doing it?
I think I just heard it was the football field.
What was it?
It's like
Yeah.
lower schools have like something.
Yeah,
About, like,
yeah.
the reenactors and the shock. Yeah.
Well, I think it's scaled down. It's
Was it
scaled
aimed,
down.
it was aimed towards the lower school. Towards our kindergarten buddies.
All right, so that, hey, set this equal to, so therefore we're going to set this equal to -1. All right, so therefore -1 over x squared is equal to -1.
Negative 1 equals negative x.
So x squared equals 1. So x equals plus or minus 1, but if you remember the solutions that we are guaranteed are those only in the interval. So we throw out the -1 solution because only 1 is in this interval. So remember that the theorem guarantees the existence of 1, at least 1 on the interval. So the one that we're looking for is the positive 1. So that's the value of c over there. Okay. Is that cool? Yeah. Okay. All right. Two true and falses.
Is there a lot of homework?
There's about 12 or 13 problems. It's like about 6. It's like about 8. I think it's 8 like that. Those kind of things, and then you've got. Well, actually, you had 4 true and falses, but I'm going to do now 2 of them. So.
Oh, sweet.
So 47. All right. The mean value theorem can be applied to f of x equals 1 over x on
True.
False.
False.
F equals 0, so you
Yeah.
have one.
Yeah, it's
one
not
is 0,
continuous.
False.
it's not
Right, it's not continuous on.
Oh, yeah, because yeah, that's what we just said. Wait, what does the MVT stand for?
Mean value.
Mean value theorem
Mean
plus
value.
valuable theorem.
That's mean value.
Most valuable teammate.
Yeah, most valuable thing. All right, so the answer here is false.
Most honorable.
All you need is one condition that is not true. So I was put false. F is not continuous. That's pretty cool. Fx not continuous on. Since F0. Yeah. All right, one more. 49. If the graph of a polynomial function has 3 x-intercepts, if the graph of a poly function has 3 x-intercepts, has 3 x-intercepts, then it must have at least 2 points at which its tangent line is horizontal. Okay, let's draw a picture of this. So, a poly function, that's just, remember polynomials are the most well-behaved functions in all of math. It's just like a little roller coaster ride guy. It has 3 x-intercepts. So let's put those in. Then it must have at least 2 points at which its tangent line is horizontal. Why can you say that? Why is that going to be true?
Because
Exactly, Rolle's theorem. Yeah, this is exactly an application of Rolle's
yeah, we're
theorem.
B stems.
True. Right, by Rolle's theorem.
Oh, that's because you count them as equal to each other and you have just 2 separate intervals.
Yeah, you could just apply Rolle's theorem right there and right here. Yeah, true. Okay, that cool?
Yes, it makes sense. I said it was true even before we drew it out.
I'm surprised it's actually false.
Okay, and we're gonna sign out now, all right? So it's on this recording.
Oh, it's still